I want to explain deep anomaly detection and attributed networks. So when we say it, in this playlist, I want to talk about the usage of, I want to leverage graph neural networks for fraud detection. So this is our application, and I mostly talk about graph neural networks because it has many applications, especially in fraud detection. So this is my motivation, and fraud detection is just an application. As you know, there are many financial frauds: bank fraud, corporate fraud, insurance fraud, cryptocurrency fraud. And when I asked the Sage what are some of the GPT-4, what are some of the types of financial fraud, it explained, for example, identity theft. Then I asked, how about credit fraud? And it continued and said, credit fraud, it involves unauthorized use of credit card, and so on. Then I asked, can I use graph neural networks for fraud detection? And it simply said that yes, you can. And so GNN for fraud detection is to represent financial transactions as graphs. And you can also use it for anomaly detection, which is the topic of today. And then I ask, what are some limitations of using graph neural networks for fraud detection? And I expected this to hear that it has limited interpretability and also scalability. Also nowadays, all these people have become very, very smart. So you should beat those kinds of bad guys. So these are the limitations of graph neural networks for fraud detection. So why do we use GNN for fraud detection? First of all, for class imbalance, also for anomaly detection. You want to handle point, structural, and contextual outliers. And you do graph embedding, those embedding that I've talked about in different playlists. And also it should be explainable, and it should also know about fairness. So deep anomaly detection, this article is really interesting, but the other two articles are not using graph neural networks. So the problem is an old paradigm. The problem of old paradigms, previous methods, is that these models cannot fully address computational challenges and attributed net. For example, they can suffer from network sparsity and data and linearity issues. So I have a solution for that it explicitly models the topological structure and nodal attributes seamlessly for node embedding learning, and it is customized to address anomaly detection. So we use deep autoencoder, and the synergy between graph convolutional networks and the autoencoder enables us to spot. So we use deep autoencoder, and GCN is just the encoder part of that. And finally, we create a score for each node of your graph. So we have, for example, of ego networks. This is your ego, and you have some blue nodes that we want to alter them. The ego node alters that. It modifies that, changes that. For example, sending transaction or so on, or sending a message in. So this is an example of attributed networks. So each node had some features that, for example, in banking, it's really important, lots of information of a person. And we can do anomaly ranking on attributed networks. We rank them, for example, which node is more and has more anomaly, and so each of the nodes has a rank. And so I will review the deep autoencoder, and the encoder we just compress it, so we have this latent representation. And finally, your output should match the input, so your reconstruction error, which is this one, this is your reconstruction error, the cost of that should be as minimum as possible. So the architecture is like this. So you have some inputs like this, but this one is just the encoder part that we use layer 1, layer 2, layer 3 of graph neural networks, and we use convolutional neural networks. So it is graph convolution. So if you watch my playlist on graph neural networks, I have explained graph attention networks, graph convolutional networks, and many other paradigms for GNN. So assume that this is your encoder, so we have a representation. It means that for each node of your graph, for example this guy, we have a vector. So we have all of these vectors, and you know that if you have vectors, you can simply create a naive transition matrix, a matrix of graph matrix, and after that, using this, you can create the reconstruction errors. So A and A hat should be as close as possible, and X and X hat should be as close as possible. And using this information of A and X, we can create the score. I will define the score. So each node, for example, this node is very suspicious. It may be the hacker one, so it has the highest score for anomaly. So we use graph convolutional networks. I've explained all of these in my place for graph convolutional networks, for GNN, graph neural networks, and so I skipped them. You know, this is A tilde is just the diagonal element, and A is just a transition, and D is the diagonal matrix, and all of them are standard coordinates. So we have 3 layers of convolution, as I said. Layer 1, layer 2, layer 3, and these are representation of layer 1, layer 2, and layer 3. So this is just the attribute network. We are just encoding that in our autoencoding model. After that, we want to reconstruct that. You want our prediction of A as close as possible to A hat. And also for the original attributes, we can just calculate the loss. The loss could be, for example, both the transitions should be similar and also the attributes should be similar. And using this information, we can say if this approximation is great, so this should be small and there is no anomaly. But if this term and this term are great, or this term are great, if these are high, then the score becomes high. It means that node VI is very suspicious. It is anomalous, and there is anomaly in that. Maybe there is a hacker in node VI with that IP address. You can find and detect it. And so anomalies are larger scores. When this term becomes large, your anomaly goes higher, and you capture the node VI for that corresponding IP address, or that person, or that credit card. So as there is no, but we want to have inductive bias in machine learning. Always we need inductive bias, because all we do in unsupervised learning is like hallucination. It just captures the main ideas, the the average values. But if we do an injection, if we do inductive bias, like this article, for example, this article uses a kind of inductive bias that, for example, says it manually creates some clicks and says that this corresponds to anomaly. For example, another click, so a set of generated clicks creates that injection that I was talking about. And these are the datasets. We use 3 datasets: blog catalog. It's just some of the blogs, and you can. So users are associated with a list of tags. For example, tag of machine learning, tag of AI, tag of graph neural networks. And here, these are the things that you can consider it as an attribute. Or in the Flickr, you can have the same kind of tags, for example. Or in ACM, you can have the kind of citation and other attributes of each paper could be considered. And these are results. You have precision and recall. F1 score, if you want to calculate F1 score, you need precision and recall. And they have done it for 3 data sets that I explained. And that's it.